Hi, I'm Will Chamblee.
Hi, I'm Victoria Woods, and this is our final project for everything that we've learned over the semester.
This is topic one, which is measurement and the density of numbers and the law of large numbers.
Okay, so my question for you, Will, is why do we feel like we are standing still even though we are moving at a very fast speed?
We feel like we're standing still even though we're moving at a fast speed because the motion of the Earth's rotation is constant, and so is like the rest of the speeds, whether it be the solar system orbit, etc. When speed is constant, you don't notice the motion. It's kind of like when you're in a car, when you're moving at like a constant speed of like 50 miles per hour, for example, you don't really notice the motion. But when you speed up or slow down or like hit the brakes, you notice the motion. And since speed is relative to what it's being compared to, it really depends. Like something can be super fast compared to something else. So
Okay. So my next question for you is how is size relative and why is it important when comparing things?
something can be big or small depending on what you compare it to. So like speed is relative. If you look at like the pictures, Um, a shrew or a hummingbird is really big compared to like a matchstick, but it's really small compared to a human. And the same can be said for like the planets compared to human, or like even a human compared to Texas. So it really is just important what you're comparing the size of something to, and that's what makes like size, whether it's big or small.
Okay, good. Okay, and one more question. What is the maximum times a number can be divided by two?
There is no maximum time; it can be infinitely divided. So if you look at the formula, um, on Excel, we just did the equal the top divided by two, and I just dragged it down as far as I could, and you see it just keeps going. So there's an infinite amount of times that you can divide a number by two.
Okay. Okay, well, what is an asymptote?
An asymptote is a line that continually approaches a given curve but does not meet it at any finite distance. So if you look at the graph on the Adderall, the line keeps going towards the zero on the x-axis, but it never is going to, or the y-axis, but it's never going to hit it. It just infinitely gets closer. But because it's an asymptote, it'll never like hit zero. So,
Okay, very good.
all right, Victoria, how can theoretical and empirical probability determine the roll of two dices?
Okay, so theoretical probability is just mathematically determining the any given number or values, including the roll of two dices. So, for example, we just did a mathematical equation to determine um, what sum or products that we can get when we roll two dices. So here we have what would be the product of 12, and we just factor that out mathematically. So you have here 6 times 2 gives you 12, 4 times 3, and so forth and so forth. And that's how theoretical probability works. Down here, I have the theoretical probability table, which tells you all the possible outcomes depending on the roll of dices, the sum and product. So for example, like if we wanted to know the sum of an even number, you have the odds, which are in your favor, the odds against, which are not in your favor, and then you have the probability, which are all the odds possible, which are also in your favor. So you have an 18 out of 18 odds of getting the sum of or getting the sum of an even number. And then you have odds against, which is also 18 out of 18. And then you have 18 out of 36 because there are 36 total possible outcomes. Empirical probability is actually testing the experiment because you can't get a true estimate when you roll a dice in real time. The values are random and they will never be the same. So what we did was create a random chart between 1 and 6 for the roll of two dices. And every time we clicked on the cell, we never got the same two values between 1 and 6. So that's how empirical and theoretical probability works when you're using two dice.
Awesome. What is the law of large numbers?
Let me click Okay. So the law of large number or central limit theorem just tells us that the larger the numbers get, the more normally distributed the data becomes. So for our empirical experiment, when we did the roll of two dices, here we have the 6 rows and then we have 6,000 rows. You can see here on our histograms with 6 bins and 11 bins that for the 6 rows when rolling two dices, the data is very spread apart. We can't get a true meaning of what those random numbers were. But when the rows got larger, when we got down to 6,000 rows, it gave us a more even distribution of data. And that's indicative of empirical experimentation because you have to keep testing it in order to get a good set of data. So that is the law of large numbers.
Awesome. All right, topic 2 is misleading and false data reports and assessing resources and information.
Alrighty, so Will, my question to you is how can charts and graphs mislead us while having correct data?
Charts and graphs can mislead us by misrepresenting the data on the graphs. For example, if you take the pie chart on the left, it makes it seem like the money the city is contributing to the arena funding is half of what the others are contributing. But if you actually look at the numbers, as you see on the graph on the right, the city is actually getting 65%. So the pie chart on the left is actually misleading you into thinking the city is giving less than it actually is, which is important because the money the city is giving is like tax dollars. So it really means that you're paying more for the arena than you thought. So that's how the graph is misleading you.
Very good. My next question for you is how does changing the starting value on the vertical axis change how the data is represented in the graph?
Kind of going back to the last slide, it's like misleading you. So as you see on the left chart, it looks like Clinton had a way higher unemployment rate than Bush did. But if you change the starting value to 0, you actually see that they're much closer. So changing the starting point to 0 gives you a way better picture of how the two numbers compare. And it gives you a chart that is way more indicative of the actual data.
Okay, very, very good.
All right, Victoria, how does data reports show correlation between GMO crops and illnesses in America?
Okay, well, GMO crops were introduced to the American population in 1996, and a physicist named Nancy Swanson started doing a lot of research and collecting data, and she found a positive correlation between the implementation of GMO crops and the increase in illnesses in Americans. So the way she provided that correlation is using the scatter plot and bar graph charts to show how when from the time GMO crops were introduced, every year that they were planted, these diagnoses went up. So that's how she is showing this correlation between GMO crops and illnesses.
Awesome. How are GMO crops reported by the FDA?
Okay, so unlike Nancy Swanson, the FDA does not have a lot of information at your fingertips. They don't have like any graphs or anything to show whether or not there's a negative or positive correlation between GMO crops and illnesses in America, which could be concerning. But they do have a lot of mission statements and things like that to assure the public that these crops are being surveillanced and regulated just like anything else approved by the FDA. We know from these reports that 144 crops have been approved by the FDA since 2012, which is a little under a decade. And then here we have the crops that have been approved. The FDA says that foods from GE plants must meet the same food safety requirements as foods derived from, sorry, I have this thing blocking my view. Foods from GE plants must meet the same food safety requirements as foods derived from any traditionally bred plants. And they say also that the FDA regulates foods from GE crops in conjunction with the U.S. Department of Agriculture and the Environmental Protection Agency. So they say that they are surveillancing these GE crops the same way, and this is how it is reported by the FDA. So correlation does not mean causation in terms of if GMO is causing more illnesses in Americans. And also you have to take in other factors. You have to take in environmental factors, racial and cultural factors, and then you have to also take in socioeconomic factors, what people can afford. So it's just good to have both sets of information.
All right. What is the probability of guessing and scoring an 80% on a multiple choice quiz?
So to find that, we use the binomial experimentation, which is a statistical experiment that is satisfied by 4 conditions, which I have listed. You have a fixed number of trials. Each trial is independent of the other. There are only 2 possible outcomes, and the probability of each outcome remains constant from trial to trial. So no matter what the outcome is, it has to be consistent. And then we have 3 distribution formulas. One is a factorial, one is provided by Excel, and the other is a combination formula. So we take we break down all the variable identifications. So X will represent the 80%, P represents the 1/4 probability of getting that answer correct. Q will tell us how many times that we can get it wrong based out of 4 possible questions. And N is the number of trials to be tested, which there are 10 questions on this quiz. So when we plug it into all the distribution formulas, we got a consistent outcome from each trial. And it tells us that there's only less than a 1% chance that you can randomly guess on a multiple choice quiz and get an 80%.
Awesome. And what is the expected outcome of buying lottery tickets?
So the buyer's expected outcome was a negative $1.93. And we got that because there's almost a 77% chance that you can scratch a lottery ticket and not get anything. So to get the $1.93, we took the amount possible of winning, which was the negative $5, and multiplied it by the probability of winning, and it gave us a negative $3.85. We added up all the expected outcome, and that gave us the average buyer's expected outcome, which is a negative $1.93. For the seller's expected outcome, that's $1.93, and that's because obviously if you're losing, then they're gaining. And we find that by multiplying it by -1, anything multiplied by -1 gives you the opposite value. So we multiplied -1 by a negative $1.93, and it gave us a positive $1.93. And then the seller's expected outcome for selling 5 million tickets is over $9 million. And that's just taking whatever these sellers are getting every time somebody loses and multiplying it by 5 million. So these are the expected outcomes for buying lottery tickets.
Awesome. Topic 3 is probability of an event given a population and a sample.
Okay. So Will, what is more likely, an American being obese or an American being obese with type 2 diabetes and high blood pressure?
So as you see in the Venn diagram, as well as the chart, an American being obese with type 2 diabetes and a high blood pressure is way more likely than an American being obese. In the Venn chart, you see 3.1% of Americans are just obese, while 8.5% have all 3 of the diseases. And if you look at the chart, you can see how we got there. So you take like the total number of Americans, and then you can see how many of them in millions are obese, and you can see the percent. And then over on the right side, we calculated how many are just obese with this formula in the middle, and then how many just have type 2 diabetes, and et cetera. And then how many have type 2 diabetes and obesity, or type 2 diabetes and high blood pressure. We put all these statistics into the Venn diagram, which gives you a good look that people with obesity usually have the other 2 diseases in type 2 diabetes and high blood pressure.
Okay, good job. My next question is, what is the likelihood of being an obese American when living in Arkansas?
The adult obesity rate in Arkansas is 35%, which is 7th in terms of states. That means that if you're an adult compared to other states, you have a very likely chance at 35% of being obese and adult.
My next question for you, Will, is what is the probability that a driver was using both cannabis and alcohol according to the Venn diagram?
So the Venn diagram, which we took from statistics, I think from Canada, shows you that that the chance of someone that someone was drinking alcohol and cannabis is 1.6%, which is 18 out of the total people that were pulled over. You see where the two bins for cannabis and alcohol overlap, which gives you the 1.6% or 18.
Okay. My next question is there a higher rate of driver fatalities on rural roads or in cities?
There's a much higher rate of driver fatalities on rural roads than cities. You can look in the graph where we just input our data. Rural roads have much more fatalities at 59 and 92 than cities or the urban Melbourne, which just have 12 and 36, and then 21 and 49. So you also see the 5-year average, which is 76 compared to 11 or 49. And this is illustrated by the graph, which we just took the data and input it into the graph in Excel. You see that rural roads have much higher bars than either urban Melbourne or provincial cities or towns.
Very good.
All right, Victoria, what is the probability of a high approval of Trump as president depending on the U.S. political party?
Okay, so basically this is considered a population sampling. We're taking Americans and breaking them down by their political affiliations, and then we're further breaking them down into subgroups by determining how many within these political factions are approve or disapprove Trump. So depending what political group you belong to, you're either the probability of approving Trump is going to be higher or lower by comparison. So for example, 87% of Republicans approve of Trump, while only about 12% disapprove Trump, which means that the probability of Republicans approving Trump is very high. But by comparison, 90% of Democrats disapprove Trump, while only 8% approve Trump. So by comparison, his approval rating based on the Democratic Party is very low. Independents also too seem to disfavor Trump. They had, they had a 63% disapproval rate of Trump and a 24% approval rate. So it's also pretty unlikely that they approve of what Trump is doing. If we wanted to get a general consensus of what the population overall thought of Trump, we would do a random highly diverse sampling and to get a climate of what the entire population thought of Trump. So, yeah.
Awesome. What is the chance of being a man or woman depending on the different branches of the U.S. military?
Again, this is another population sample. This time, we're determining this sample based on men and women in America in the U.S. military. So the way this works is that once we find how many men and women in the U.S. military, we then can break them down by military branches, which are subsections. And here we have the total. There are over 1 million men and women in the U.S. military. And then we have the percent of women and the number of women in total. And then in the different branches, Army, Navy, and Marines, and Air Force. And then we have the percent of men in total and the percent of, or the number of men in total in the U.S. military, and then broken down into these branches as well. So for example, if we wanted to know the probability of men being in the Army versus women, we could say that it's more likely that men would be in the Army than women because men have a 68%, men are in the Army 68% and women are 32%. So they're more likely to be in the Army. And then down here, we have what is called a conditional probability chart because it's asking us what is the probability of like having a woman in the Air Force, Marines, and Navy and not the Army. Well, to know that, we are implicating or implying that there are women overall in the US military. That's the condition. In order to know how many women are in these different branches and not in the Army, we have to acknowledge that there are women in the Army. So we have to find that first. So it's like A occurs given that B has occurred. So the probability of a woman being in the Air Force, the Marines, and the Navy, and not the Army, there's a 33.3% chance. And then the probability of a man being in the Army, there's a 34.8% chance. So that's how conditional probability works. And that's how you can negotiate the chances of men and women being in different branches in the U.S. military.
Okay. Topic 4 is population, samples, probability, and distribution.
Alrighty. So, Will, my question for you is, why are the standard deviations so different between the Army recruits and the mall shoppers?
So the mall shoppers have an outlier, which is this 72.5. You can see it on the graph to the right. It has the number way up there. The outlier skews the data, which includes the standard deviation. While you look at the Army recruits, there are no outliers, which means the standard deviation is going to be a lot tighter. See, all the dots are really close to the line. Mm-hmm. This most likely has to do with the fact that the Army recruits are usually, since they have like a fitness test to get into the Army, their BMIs are going to be very similar. When you compare it to the mall shoppers, there's no like fitness test or any requirements to get into the mall. So you're going to see a much higher spread, including some outliers in the random mall shoppers. So.
Okay, very good. So my next question for you is, how do the box and whisker plots and scatter plot trends correlate to the size of the standard deviation and the coefficient of variation?
So the dots on the scatter plot for the Army recruits, which is on the left, are much closer to the trend line, as we saw on the last slide as well, indicating that it has a smaller deviation. On the random mall shoppers scatter plot, again, you can see the dots are all over the place with the outlier as well, indicating a larger standard deviation and coefficient of variation. So that also correlates with the box and whiskers plot. On the Army recruits BMI box and whiskers plot, you see that the box is much smaller instead of the whiskers. It's way more condensed in between the 30 and the 10. And when you compare that to the random mall shoppers, see the box is a lot larger and the whiskers are a lot larger, covering a larger set of numbers. And then you also see this dot, which indicates the outlier. And that correlates, the bigger box correlates to a larger coefficient of variation and larger standard deviation, especially when compared to the Army recruits.
Okay, very good.
Which age group is most likely to have a fatality occur while driving?
Okay, so according to the Transportation Accident Commission report, the age group that has the highest driver fatalities between 2018 and 2019 are 70 and over. They had 17 fatalities in 2018 and 33 in 2019. But a close second was the age group 50 to 59. They had a fatality. Their fatalities in 2018 was 20, and in 2019, 21. So these are the age groups that are most likely to have the higher fatalities while driving.
Okay. How does urbanization influence driver fatalities in the U.S., and can this information be projected onto any city or country?
Okay, so again, according to the Transportation Accident Commission report, rural roads have the highest accidents and fatality rates in America. There are 53 in 2018 and 90 in 2019. A close second were the urban Melbourne, what are like downtown areas, metropolitan areas. That was 33 in 2018 and 41 in 2019. And provincial city and towns had the least amount. So basically, the less underdeveloped the infrastructure are, and especially in inclement weather, the more prone they are to accidents. And this information cannot be projected onto other cities or countries or anything like that, because the level of urbanization may be different depending on where you live. Like, for example, in British Columbia, there are smaller, denser population and they're more metropolitan. They also have a higher level of urbanization and public transportation. So they're less prone to having accidents. So you can't project their data onto America's, and we can't project our data onto theirs.
What is the probability of belonging to the percent of the US population that has a healthy BMI?
Okay, so because I'm a girl, I just went ahead and went with the women's. So the average BMI for a woman in America is 27.7. The standard deviation is 6.15, and the confidence interval is 0.15 plus minus 0.40. Now we know the mean is the average, the standard deviation is how spread apart the values are, and the confidence interval is how certain the true mean is to lie within the set of values. So we know that this is a strong confidence interval because 0.15, sorry, 0.15 is just 15.4 and 0.40 is just 40. And those are two standard deviations away from the mean. So we know this is a strong confidence interval, and this average is the true average. This is the true mean. This is the BMI for women, average BMI for women in America. We got this bell-shaped graph by using the fourth standard deviation on the standard deviation chart. We used the normal distribution formula in Excel, and then we used the z-score, and it gave us the chart. Now, the probability of belonging in a percent of the US population that has a healthy BMI is actually very slim. According to the National Center for Health Statistics, we are in a bit of an obesity epidemic. Obesity in America for adults, both men and women, is 39.8%. And that's like 93.3 million Americans overall. And then, like you said, in Arkansas, our BMI is 35%, which is at the very top. Then the obesity rate for the ages between 26 and 44 is 40.3%. So it's not very likely that we would, given American or Arkansan, would be in a healthy BMI range.
What is your z-score, and how does it determine your BMI and where you rank comparatively to others?
Okay, so the z-score just measures how far apart, how many standard deviations away from the mean that you are. So in this case, the mean is the average BMI for both men and women. For women, it's 27. For men, it's 29. So depending how far you deviate above or below, the mean tells us where you fall on the BMI range and if you're going to be in that average or healthy BMI range. We find our z-score by using the z-score formula, which is down here. You have z equals x minus the mean divided by the standard deviation. And in this case, the x value is represented by our BMIs. When we plug that in, we get our z-score, and then we can corroborate that by using the z-score charts. So my z-score was negative 1.25, and that made me one deviation below the average for women, but still within the healthy range. My boyfriend's was a negative 1.48. He's about 2 deviations away from the men's average BMI, but he's still within a healthy range. And then my sister Kimberly's was a negative 0.60. She's right within the healthy range. And this is how we were able to, the z-score was able to help us compare our BMIs and where we fit on the scale.
All right, topic 5 is personal, state, and federal finances.
Alrighty, so Will, what are the outliers that keep American income and distribution from being normal?
So there's one major outlier, and that's the top 1% and really the top 10%. But the major one is the top 1%, which owns about 35% of the American wealth. You can see on the chart at the bottom that the top 5% owns a large amount of the wealth. So you have this chart that looks like it has a normal distribution until you get to the top 5% and really just the top 1%, which of course skews all the data like we learned a couple of slides ago. It makes the standard deviation and mean and stuff like that unusable. So that's what is really skewing the American wealth distribution.
Okay, very good. My next question is, how many sales did it take for this company to break even?
So you can see on the chart to the left with 0 sales, that's the start. And then at 100 sales, in the red, you can see that's the bottom point where they were making the least amount of money, really losing the most money. And then they break even right at the 200, which is in green, which is, if you look at the chart, it has this kind of opposite bell-shaped curve, and where it passes the profit line at 0 is right before 200 sales. So I put it right at 200 sales, and you see it just continues to grow. To calculate this, we use the formula, which you can see at the top of the graph and of the chart, which is 6.212 with the amount of sales to the second power, and then you just minus that by 1200 with the number of sales minus 12,000. And that's how you can get the profit margin of the company.
Okay. So what percent of the U.S. wealth does the top 1% own?
So we kind of talked about that 2 slides ago, but it owns 35% of the wealth, which you can see on this chart. There's 1%, which is the orange, the amount of people, and then the blue is the amount of wealth they have, which is right at 35, which is a lot of money, of course. And you also look at the top 10% owns 76.7% of the wealth in America, compared to the bottom 40%, which is at the far left of the graph. You see the orange, which is the amount of people, and there's the little sliver of blue, which is the amount of wealth they have. It actually comes out to negative 0.9% of the wealth in America.
Very good. My next question for you is, where is the highest percentage of the U.S. tax dollars spent?
So the highest level, or the highest percentage of U.S. tax dollars spent on Medicare, Medicaid, CHIP, and marketplace subsidies, which is the yellow in the pie chart. You can also see on the graph, a close second is Social Security at 24%, and then Defense International Security System at 16%. And then you can see all the smaller programs that they're still spending money on. I thought it was really interesting that education only gets 2%, which is obviously more interesting to us because we're in college and stuff.
Yeah.
But it seems like such a small amount compared to other stuff like safety net programs or transportation infrastructure and stuff like that. All right, Victoria, what are some of the differences in 3D graphical images depending on rotation and perspective?
So a 3D graph will change depending on the number values, how big or small they are, and also how you rotate the graph. So for example, this is the graph that I made down here under the number pattern. I didn't repeat any numbers, so it gave me this sort of linear plane. And I gradually added larger numbers in my number chart, which gave me these peaks, because the graph is always going to force perspective relative to the size of the number. So when I did that, it gave me these really nice pyramid peaks on my graph. When you change it on the x-axis or the x rotation, you're going to get a 360 view of the graph. So when I changed my graph around, it gave me sort of an almost 2-dimensional plane, but it also gave me, shifted the way that these peaks looked on the graph. So they look more condensed and more like pyramids, I guess. So when you change it on the Y rotation, or the Y axis, you're going to see very high above and very far below the graph. This is beneath the graph, and you can see it looks almost 2-dimensional again, but you can see the 3D effect from the peaks underneath the graph. So the perspective is always going to change depending on your number pattern, the rotation of the graph, and how you force perspective depending on the values of the numbers.
Okay. What is the distribution of wealth in America?
Okay, we just talked about that. But according to Pew Data Research Center, the top 1% has 35% of the wealth, while the lower 40% only has less than 1% of the wealth. I actually learned that income inequality in America has the highest rate of income inequality in a first world or developed country. And so you have a lot of people that are living right at the poverty line or below it, or working class poor. So that just kind of gives you perspective about how people are living in America. Most people cannot make ends meet. Most people do not have accessibility to proper health care, education, transportation, housing, or anything like that. So this is how the distribution of wealth in America looks like for us.
Mm. Okay, and topic 6 is interest, investments, and loans.
Okay, so why is the growth pattern of a simple interest line linear and not exponential?
The growth pattern of a simple interest line is linear because the interest is on the principal amount and not based on the amount that you paid in the last month. So the interest rate of 6% is always applied to that 3,600, and which we'll talk about in the next slide. A compound interest is different, and that's what gives it an exponential growth. So the linear growth means that the line just stays straight because the amount of interest is the same each month. So you're really paying the same monthly fee each month.
Okay. So what makes the growth pattern of two compound interest exponential?
So with the quarterly compound, basically what's happening is you start off paying 6% interest on that 3,600 number. But then the next month, which is going to be, it's actually going to be quarterly, so 1/4 into the year, you pay interest on the 3,816. So your interest, the amount you're paying is going up each month, which is the interest compounding. And the same is with the continuous compound. You're paying that 6% interest, not on the principal, but on the amount you paid last month, which causes the lines to have an exponential growth, which means they're always getting higher. They're more rapidly growing and not staying at the same rate like a linear line would.
Okay, very good.
Okay. How does interest affect monthly payments on a home mortgage and what you pay overall for the home?
Okay, so depending on your mortgage loan type, which is the years, the principal amount that you owe, and your interest rate, you're either going to pay a larger monthly fee to pay it down your loan in a shorter amount of time and pay a lesser amount of money overall on your home and your interest, or you're going to take out a lesser monthly loan, but a larger monthly loan type in years, and you're going to end up paying more money overall in interest. So for example, here, if we had a mortgage loan type of 5 years based on the principal of $110,000 that we have to pay back, our monthly payment would be about $2,000, but overall we would be paying comparable to what we paid buying the house, and also the interest rate is lower. But if we took out like a monthly, a loan type of 30 or 35 years, we'd be paying less money monthly, but overall we would be paying twice as much money on the house overall and for the loan. So it really depends on, what you're willing to pay every month.
Awesome. How does extra monthly payments affect the payback of a loan?
Okay, so like I said, if you don't put any extra money towards your monthly payment, it takes a longer time to pay it off, and the overall you're paying will be more. The more money you put down towards your loan monthly, $50, $100, the larger your monthly payment is, but the least amount of time you spend paying it off and paying for it overall. And you can see that better explained in the bar graphs for the total amount of interest on loan. If you pay more, you have a lesser interest rate, but if you pay nothing, you have a higher interest rate. If you pay more a month, you take a shorter amount of time paying it off, versus if you paid nothing for it monthly at all, any extra money monthly. And then also with the total amount paid, you see that there's less on the total amount for the 100 extra, where for the no extra amount has the highest total amount paid. So again, it just depends on what you're willing to do every month for a loan.
Yeah. How does the cost of living compare city to city?
Okay, so for the three houses that I chose, I found that the cost of living is pretty comparable for all three houses. The house that I found in Dallas, Texas, it was the cheapest and it had the cheapest mortgage and loan on it, but it came out to have the same amount of total expenses monthly because of the state taxes. The state taxes in Texas is like, let me see, 8.25%, but it's only 6.9% here in Arkansas. So it actually pays more to live out in Arkansas in terms of Texas, in terms of state taxes. And so even though I thought I was like getting a deal with this cheaper house and the cheaper mortgage, the state taxes made up for that. So it made the cost of living for all three houses comparable. And then the median price for homes in Arkansas is about the same, which is why it'll always be comparable to the salary that you make.
Hmm.
So from city to city, it's about the same, honestly.
Okay. And how does cost of living affect leftover income?
Okay, so like I said, let's say if I chose a house and I chose the house in West Little Rock, now we're talking about paying on a loan because I bought this house. So now we have that loan to pay back. Then we have the state taxes, and then we have, the car note and things like that. So leftover, you never really have leftover income. You can only project so far ahead in the future and know exactly what your expenses are going to be. This is just kind of hypothetical. You still have to budget, and you still have to budget your expenses. And so you never really have leftover income. It's always going to go towards some sort of expense.
All right. So that's our final project.
That's it.
Thank you guys for watching.